Okay, hello class. So this is my presentation for homework 11. So we exercise 10.5 on our most recent chapter. Yeah, so let's just dive right into it. Here's our problem statement for 10.5. We have a function from R2 to R, and let the point xy, f of xy be the surface in R3 given by this function. So then we're supposed to show that if we have L, the linearization of the function at some arbitrary point, and we have the point in R3 given by x, y, and that linearization function, then that point describes the tangent plane to the original surface. So that'll be in 3 dimensions, x, y, and z. Okay. So basically, we need to unpack a lot of notation here before we can really start to see how these are connected. Let the linearization of f at this initial point p0 be given. We have this definition in the text that we find the derivative at f at p0 if we have some defined notation or notion of the derivative. And then we shift some arbitrary vector in our input space by the initial starting point p0, and then we take the original function evaluated at p0. Okay, so that's just a lot of notation to unpack. First thing we want to look at is this derivative term. So for a function from R2 to R, we have the gradient, or nabla, or del, however you want to call this, as a defined notion of the derivative of f, which we can evaluate at our starting point p0. So then for our term d, the derivative on f, we're going to just replace that directly with del, or nabla. So the gradient of f at p0. All right, and then so we just want to unpack this notation a little bit further. First thing I want to notice is that, L, our linearization term, is a function of x and y. So, in R3, we just call that point z. So then when we look at this gradient term, we'll have, the partial derivative with respect to f, or with respect to x of f at the starting point, and then we'll have the partial derivative of f with respect to y. For the shifted terms, just have, an arbitrary xy shifted by x naught and y naught. And then our, linear, or f at p0 term is just going to become z0. So, that's go along with our replacement of f to z. So this dot product is fairly easy to see. And at this point, if we're familiar with Calc 3, brushed up on any of that material or familiar with it recently, you'd see that this is the equation of a plane in R3. It's probably a little bit easier to see this, or I know it was easier for me to see this in Calc 3 if we look at it sort of more from a vector operations standpoint. So we'll bring z to the other side and look and solve for 0, more or less. And then we see that this is can be written as a dot product between two vectors. The interesting thing to see here is that, for this plane, the direction vector, the normal vector, is given as our first term with the partial derivatives. And then the point in the plane will, you could think of it as starting at x naught, y naught, z naught, and then just going to some arbitrary point in the plane. And what we want to see is that these two vectors are orthogonal. So that means the vector, that goes from our initial point to xyz in the plane is always going to be at right angles, orthogonal, or basically tangent to the function at this point p0. So that's the main point. And so now at this point we could use this to kind of solve a problem. So I think just to solidify things, we'll look at the next question in the homework. That'll be 10.6. So we're given a surface in R3 given by the function f of xy is sine of x plus cosine of x, and our starting point will be at pi over 2 minus pi over 2. So we'll just import the definitions directly from above. We have the gradient of f at p, shift some arbitrary vector in the space by p, and then we evaluate f at p as well. So this dot product we can see, because cosine of pi over 2 is 0, evaluates to be fairly simple. And just to kind of prove that that's what the answer should be, I've made a little visualization here for it. So we see f of xy is sine of x plus cosine of x. And then I've given the point in R3 as just X, Y, and then our linearization term here. And we see that that point is, if I can zoom in maybe a little bit without breaking too many things, we can see that that point or that plane is directly tangent to the surface at that point. All right. And so that's all I've got for today. And I hope you guys have a great class, and I'll answer any questions or comments whenever we see each other again. I'll talk to you later.